In this video, we are going to discuss and define buffer solutions. So first, let's start with a definition of a buffer solution. A buffer solution is a solution which resists dramatic changes in pH. So if you have a buffer solution and you add some acid or base to the existing buffer solution, the pH of that solution generally should not change dramatically. A buffer solution is prepared by combining a weak acid and its conjugate base. So we have here 4 examples of how to prepare a buffer solution. You could combine acetic acid with its conjugate base, the acetate ion. Now, of course, you could not add just the acetate ion. You would have to add something like sodium acetate or potassium acetate, some salt of the acetate ion. You could combine hydrofluoric acid with perhaps sodium fluoride, potassium fluoride. You could combine ammonium chloride with ammonia to create a buffer solution, again a weak acid and its conjugate base. You could combine H2PO4 minus or something like sodium bisphosphate with sodium hypophosphate. Those two would create a buffer solution. So again, any combination of a weak acid and its conjugate base would generally produce a buffer solution. Now, how does a buffer solution resist changes in pH? If you add a strong acid or a weak acid, or excuse me, an acid or base to the buffer solution, how does it resist change in pH? Well, here we have a buffer solution. Let's say we have acetic acid, and we also have some concentration of sodium acetate, so we have its conjugate base. Let's say that we added a strong base to our buffer solution. If you added a strong base, which here we're representing as simply hydroxide ion, if we added a strong base to our buffer solution, the strong base would react with the weak acid. In this case, the strong base would react with the acetic acid. And what would happen is the strong base would get neutralized, or it would react with the acid to form water, and of course the conjugate base. So in other words, by adding the strong base doesn't just sit around and increase the pH. The strong base gets neutralized by the weak acid that's present. So the pH would not change dramatically. Also, you could add a strong acid to a buffer solution. If you added a strong acid to a buffer solution, the strong acid would react with the conjugate base that is present. The strong acid would get neutralized. In other words, the strong acid would donate a proton to the conjugate base, forming water, which of course is neutral, and some concentration of the weak acid. So adding a strong acid to a buffer solution, the strong acid reacts with the conjugate base. The strong acid is then neutralized, and the pH remains relatively constant. So again, be sure you appreciate how a buffer solution works, and you can show that using balanced chemical equations. So to sum that up, or to reiterate that, here we have our original buffer solution containing a weak acid and its conjugate base. When hydroxide is added to the buffer, the hydroxide gets neutralized, so the conjugate base concentration increases slightly. If a strong acid, hydronium, is added, some of the conjugate base is neutralized, and therefore the concentration of the weak acid gets increased slightly. But overall, the pH, the concentration of H3O plus, does not increase dramatically. So as long as the concentration ratio of the weak acid and conjugate base stays close to its original value, the pH doesn't change that much. A few definitions related to buffer solutions. The buffer capacity, we often use that term, and that's the ability of a a solution to resist changes in pH. So some buffers are more effective or more effective at resisting changes in pH than others. So some buffers have a higher buffer capacity. The most effective buffering, or the greatest buffer capacity, occurs when the pH of a solution is equal to the pKa of the weak acid used in the buffer. So generally, if you have a buffer solution containing a weak acid, and the weak acid has a pKa, let's say of 6.5, that buffer solution is going to be most effective when the pH is around 6.5, give or take. If you have a buffer solution containing a weak acid with a pKa of 3.0, it's going to be the most effective or have the best buffering capacity at pHs around 3.0, around that pKa. And the reason for that is when the solution pKa is equal to the pKa of the weak acid in the buffer, at that point the concentration of the conjugate acid and the conjugate base are at their maximum. So you're able to absorb more hydroxide or more hydronium because your concentrations of weak acid or conjugate acid and conjugate base are at their best. So again, to sum that up, the most effective buffering range is when the pH value is equal or close to the pH of the solution, generally within 1 pH unit. Let's take a look at a problem to kind of demonstrate how buffers resist the change in pH. Here we have a carbonic acid. The carbonic acid buffering system is used to maintain a relatively constant pH in blood. And buffers are incredibly important in biochemical systems, maintaining the constant pH in your blood, in your cells. So the first one, what is the pH of 0.1 molar carbonic acid? And you're given the Ka value in water. So in the first one, here we just have carbonic acid, none of the conjugate base. So we don't have a buffer solution in part A. What would be the pH of just putting 0.1 molar carbonic acid in water? In part B, you're asked what is the pH of the same 0.1 molar carbonic acid solution in water, but to this one you add some of the conjugate base. You add 0.1 molar sodium carbonate. So what would the pH of just the weak acid be? What would it be? And what would the pH of that same weak acid solution with the conjugate base be? So pause the video and see if you can solve these two problems and compare the pHs. Okay, so let's take a look at the first problem where we just have the weak acid and none of its conjugate base present. First thing I would do with a weak acid, I would write the correct chemical equation showing the weak acid plus water forms hydronium ion plus the conjugate base, and would set up an ice table. Here we have the initial concentration of my weak acid, which was given. Water, we don't need to worry about its concentration. Since it's a pure liquid, its concentration remains constant. Initially, before any dissociation occurs, the concentration of our conjugate base and of the hydronium, both of those we can assume to be 0. As the dissociation occurs, the concentration of our weak acid will decrease. We'll call that minus X. The concentration of our conjugate base will increase, and the concentration of the hydronium ion will increase. We'll call those plus X. And this is a 1-to-1-to-1 stoichiometry. At equilibrium, my weak acid, the concentration has dropped from initially 0.10 to minus X, so that will be my equilibrium concentration. And the concentration at equilibrium of my conjugate base, we'll call that X, and hydronium, we'll call that X. So since now we are at equilibrium, we can set up an equilibrium expression for this particular weak acid, which would be Ka is equal to the concentration of the conjugate base, conjugate base in hydronium, divided by the concentration of my weak acid, undissociated. products over reactant. Again, water is not included in that expression. I plug in my equilibrium values and my Ka. Ka is given in the problem. My equilibrium values of my products are X and X, and my equilibrium of my reactant, my weak acid, is 0.10 minus X. Now, since this is a weak acid with a very small Ka, it doesn't dissociate much. So let's assume this minus X is negligible. So we'll ignore this minus X, and our equation simplifies to 4.5 times 10 to the minus 7 is equal to X squared divided by 0.1. This makes it a little easier. We don't have to use the quadratic equation. And we can solve X, and X gives me 2.1 times 10 to the minus 4 molar. Okay? That X is also equal to the concentration of hydronium. So my concentration of hydronium for this weak acid at equilibrium is 2.1 times 10 to the minus 4 molar. I can now readily calculate the pH. If I know the hydronium ion concentration, I can take the negative log of that, and the pH would be 3.67. So we have a very acidic pH, which is expected. We put a weak acid into water. Let's look at the second part of that problem. Remember, in the second part, we have the same carbonic acid solution, but we have some initial concentration of our conjugate base. We've added sodium bicarbonate to that solution when we were preparing it. So we prepared a buffer solution. So let's set up the same type of table. So here we have essentially the same equation that we had in our first problem, except instead of our initial concentration of the bicarbonate ion being 0, we have added sodium bicarbonate to a 0.10 molar concentration. So we have some initial concentration of the weak acid and the conjugate base, making a buffer solution. Our initial concentration of hydronium we can assume to be 0 since no dissociation has occurred yet, and our concentration of water is constant since it's a pure liquid. As our weak acid dissociates, its concentration will decrease, minus X, and our concentrations of conjugate base and hydronium will increase, plus X. Again, the plus X, it's a 1-to-1-to-1 molar stoichiometric relationship. So these are all 1-to-1-to-1 relationship. At equilibrium, once our dissociation has reached equilibrium, the rate of the forward and reverse reactions are equal. Our equilibrium concentration of our weak acid is 0.10 minus the change, X, and our concentration of conjugate base at equilibrium is the initial plus X, 0.10 plus X, and hydronium is initial plus X, or just X. Since we're now at equilibrium, we can set up an equilibrium expression, a Ka expression, which would be the same as it was for the first part of the problem. Products over reactant, water is not included since it's a pure liquid. Plug in your equilibrium concentrations, and our expression becomes this. Ka is the same since we have the same weak acid. Our plus X here and minus X value here, though, we can assume those to be negligible. Since we have a very small Ka value, we can assume very little dissociation, and we have a fairly large or relatively large initial concentration. So the amount that we're losing from our initial or gaining here is going to be negligible. So our Ka value, a K expression, should simplify to 4.5 times 10 to the minus 7 is equal to 0.10x divided by 0.10. Our 0.10s can cancel, and we end up with x is equal to 4.5 times 10 to the minus 7. That is equal to our hydronium ion concentration. We can now calculate the pH if we know the hydronium ion concentration. The pH is the negative log of that, and we get 6.35. So let's compare those now. We don't want to just solve problems. We want to understand what our numbers mean. If you just put carbonic acid in water at this concentration, the pH would drop significantly from neutral, from 7. It would drop all the way to 3.67. If you put carbonic acid in water, but you added some of the conjugate base, the pH would drop, but not significantly, or not as significantly, I should say, from 7. So pure water is a pH at 7. The pH would drop to 6.35. So it would decrease because we have an acid in there, but not nearly as much. So the addition of the conjugate base to the solution of carbonic acid, in other words, we created a buffer solution, that significantly increases the pH, or better said, it prevents the pH from changing significantly, and it significantly increased the pH from when we compare it to just the pure acid in by itself. In other words, why did the pH not decrease quite as much? The weak acid dissociated less. If you have less dissociation of the acid, then the pH is not going to drop as much. So this phenomenon is what's called the common ion effect. The common ion effect is when you add the common ion, in other words, the conjugate base, to a solution of a weak acid. The pH remains fairly stable. In other words, the common ion effect is another way of saying that you have a buffer solution. So why did the pH not drop as much? Well, we can explain that using Le Chatelier's principle. If you just put carbonic acid in water, it's going to dissociate to some extent. In other words, the forward reaction will occur to some extent, and then you'll eventually reach equilibrium. However, by adding some concentration of the conjugate base, Le Chatelier's principle tells us that by adding that, we cause the equilibrium to shift back to the left. So by adding something over here, the equilibrium will shift to the left. So what happens when the equilibrium shifts to the left? You produce more of the undissociated acid. In other words, you get less dissociation of your weak acid. So by adding the common ion effect, or by adding some of the conjugate base, you cause the reverse reaction to occur to a greater extent, resulting in less dissociation of an acid. Less dissociation of the acid, you have a higher pH relative to a solution of the acid by itself. So buffer solutions are very important biologically, chemically, and we're going to do a lot of calculations involving buffer solutions. And there's actually a simpler formula that we can use to calculate the pH of a buffer solution. And that equation is what's called the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation, as you'll see in just a minute, is an equation that's used to do all kinds of calculations related to buffer solutions. This Henderson-Hasselbalch equation is derived from the Ka, the equilibrium expression for a weak acid. So let's say we have some weak acid. We put it in water, it dissociates, and eventually it reaches equilibrium. So you have the weak acid, the hydronium ion concentration, and its conjugate base. All of these are present. We could write our equilibrium, or Ka, expression for that, as shown here. We can rearrange this to form the Henderson-Hasselbalch equation. Let me just walk you through that. First thing we would do, we have our equilibrium expression. We could solve this for the hydronium ion concentration. So we've just algebraically manipulated it, so we have the hydronium ion concentration out here. Next thing we could do is take the negative log of both sides. Take the negative log of hydronium, the negative log of Ka, and the negative log of the acid over base concentration. If we do that, the negative log of hydronium is pH, negative log of Ka is the pKa, and if we take the negative log of the acid to base concentration, or acid to base ratio, we end up with plus the log of base over acid. So the Henderson-Hasselbalch equation tells us that the pH of a buffer solution is equal to the pKa. The pKa is the pKa of the weak acid in the buffer solution, plus the log of the concentration of the conjugate base to the concentration of the weak acid. And So these, the concentration of base and concentration of weak acid, these of course are your equilibrium or final concentrations. So the Henderson-Hasselbalch equation is a very powerful equation. We can do a lot of other things other than just calculate the pH of that, and we'll show you some of those problems later. You want to certainly practice some of these problems, as many as you can from your text. Get very comfortable not just solving problems with this equation, but appreciating when to properly use the equation. So give it a try and practice as many problems as you can.